Can you see my presentation?
Yes, sir.
Okay. In the last class, we have discussed about different layers of a convolutional neural network, and today we will see some vocabularies which are used as entities, important entities or components in convolutional neural networks. So one such entity is known as the stride. Now, what is stride? So here the stride denotes the number of pixels by which the window moves after each operation. Okay. So here window means the filter. So here window essentially means the filter. So how many pixels we can move? So that will be decided by the stride function. So for a convolutional or pooling operation, so we can apply this stride. We can apply this stride function. So which is nothing but the number of pixels by which the filter or the window or the mask will move after each iteration or after each operation. That means in every step, we will move the window either by 1 pixel or 2 pixel or 3 pixels or more than 3 pixels. Now here we are, let us consider here we are considering 3 by 3 filter, and in 3 by 3 filter here we have considered the stride dimension 2 pixels. Okay, so here you can see the stride dimension is 2 pixels. So whenever we will move our window or the filter, then we will consider 2 pixels stride uh, distance, and these 2 pixels every time or every step we will move these uh, 2 pixels stride by filter or window. So here you can see that this is the initial position of the filter. Then after moving 2 pixels apart, so we can get this filter now at this position. That means these 2 pixels apart, we are moving our filter. And similarly, after having the filter position over here, now again we are moving the filter to a pixel stride. Okay, so again we are moving the 2 pixels stride. So this could be 2 pixels, this could be 1 pixel, this could be or more than 2 pixels. So this is the stride. Now another important component is the zero padding. So this is another important vocabulary for convolutional neural network. Now what is zero padding? Now this zero padding denotes the process of adding p number of zeros to each side of the boundaries of the input image. Now let us consider this is the input image. Now here we can add the zeros to all the 4 sides. That means top, bottom, left and right. So all 4 sides will be considered for zero padding. So we can add p number of zeros. Now the length of the zero padding may be 1 pixels length or 2 pixels length. Now according to the filter dimension or the stride size, so we can decide whether zero padding is necessary or it is not necessary at all. So this is decided by the dimension of the filter and the dimension or length of the stride. Okay, so here you can see that here p is found to be 0. That means here we are not adding any zeros to all the 4 sides. But in case of second example, here we could see for the sake of filtering operation or for the sake of stride operation, here we are adding 1 pixel length of zero padding on the right hand side of the pixel and on the bottom. So on the bottom and on the right hand side, we are adding one pixel length zero padding. So by this way, we can adjust the dimension. Okay, we can adjust the dimension of the image first by adding the zeros to any sides of the uh, top, bottom, on left or right, or any two sides, or we can add the zero padding to all four sides. Now adding this, sometimes we can add one pixel length zero padding on two sides or one side, and on other one side or other two sides we can add 2 pixel length zero padding. This means in this pixel values, in this pixels, the pixel values will be 0 in this zero padding. So simply we will add the zeros to these imaginary pixels, and we can add these zeros to any side of the input image. So how to get the start and end of the zero padding? So this is the formula. So in this starting point of the zero padding, here we can determine the starting position of the zero padding by this formula. So here S of I by S. So here S denotes the stride length. Here I denotes the dimension of the image. So here I by S. So we are taking the ceiling. So ceiling of I by S we are taking, and minus I. Here I denotes the dimension of the input image, and here F denotes the dimension of the filter. Again, we are subtracting the length of the stride from this summation. Okay. So this will give us the starting point of the zero padding, and similarly we can get the end point of the zero padding. Okay. Now padding such this padding will give that the feature map size will have I by S. That means here we are considering the ceiling of I by S, and output size will be convenient. So this is called the half padding. This in case of the second case. So here this padding is called the half padding. Why it is called half padding? Because here we are adding the zeros only two sides, on the right hand side and on the bottom of the input image. And here we get the maximum padding. Okay, we get the maximum padding. Now how many zeros we will add, whether it is 1 0 padding or 2 0 paddings. So this will be decided by the number of convolution operation that we will perform, dimension of the filter, and the length of the stride. So all these three parameters will decide whether we should add the number of zeros to all the sides of the input image, or only one side of the input image, or two sides of the input image, and how many zeros should be added to the all four sides of the input image. So this will be decided by three different parameters. Now here you can see the how stride operation is performed. And here in the first case, if you consider this case, then here you can see that only here we are performing the convolution operation, and here we are performing stride 1 operation. Okay, stride 1 operation. Okay, and whenever we decide the deceptive field, so deceptive field, here you can find the dimension of 3 by 3. Okay, so this 3 by 3, this deceptive field decides the 3 by 3 neighborhood in the input image. So this is the input image, and this is the feature map. Okay, So every neighborhood area is mapped to one pixel in the feature map. Okay, so here actually here we are performing 4 convolution operation, and this 4 convolution operation maps to these 4 pixels in the feature map. Okay, so the feature map that we obtain in the output will give us 4 pixels. That means the dimension of the feature map will be 2 by 2. And if we consider the second example, this example, then in this example we can see the stride length is 2. Okay, and how many convolution operation we are performing? Here we are performing 4 convolution operations, and this 4 convolution operation gives us the 2 by 2 dimension feature map in the output. Okay, so each neighborhood area is having 9 pixels in the input image, and this 9 pixels is mapped to 1 pixel in the 2 by 2 dimension feature map. Now if we consider the third example of both stride and zero padding, so here you can see that here we have added one length zero padding on each side of the input image, and here we are performing the convolution operation including the area of zero padding. Okay, and similar to the first and second example, here we are considering 3 by 3 deceptive field, and according to the 3 by 3 deceptive field, the 3 by 3 neighborhood area is determined or defined in the input image including the zero padding area, and we are performing the convolution operation. So why we need to add this zero padding? Sometimes we need to add the zero padding to get the same dimension of the feature map as that of input image. Okay, now if we want to keep intact the dimension of the feature map in the output, then we can add the zero padding. Okay, or sometimes we need to reduce the dimension of the feature map after adding a zero padding, so that can also be done. So here you can see that here one stride is working. Okay, so here we perform one stride convolution operation, and here we are moving in this example, in the last example, we are moving the filter with 2 stride length. Okay, 2 stride length, and in this case we are reducing the dimension of the feature map in the output. So dimension of the feature map is obtained as 3 by 3 dimension. Okay, ক্লাসে আছে ঠিক আছে হ্যাঁ ঠিক আছে So these are the examples of convolution operation, stride, and how we can use the zero padding in order to get the identical dimension of the feature map in the output, as well as reduced dimension of the feature map by increasing the length of the stride. Now, if I denote I as the input image, which is the length of the input volume size, and f is the length of the filter, okay, and p is the amount of zero padding, s is the stride, then the output size, here the output o means, here o denotes the feature map. Okay, then the dimension of the feature map becomes determined by this formula. Okay, by this formula, if we know the dimension of the input image, if we know the dimension of the filter, if we know the starting point of the zero padding, if we know the end point of the zero padding, and if we know the length of the stride, then we can determine the dimension of the feature map in the output. Okay, so here you can consider that here if we consider this input image, then here we have added 2 length zero padding on each side of the input image, and here we have determined the starting point of the padding, zero padding, and end point of the zero padding horizontally and as well as vertically. Okay, and this is the length of the filter. Okay, and when we convolve this filter across this input image, okay, then we can obtain the feature map of dimension. This is the dimension O by O. So this can be considered as the square dimension of the feature map. And in this feature map, here we are reducing the dimension of the input image, and whatever the image properties will be observed in the feature map will preserve all the characteristics of the input image. Okay, that means these pixels or these transform features which are found in the feature map will preserve the image characteristics of the input image. Now, what would be the complexity of the model if we consider the different layers in the convolutional neural networks? If we consider the stride, if we consider the length of the image, if we consider the dimension of the filter, if we consider the length of, if we consider that how the convolution operation will be done. So, considering all these operation and the different layers, so we can estimate the complexity of the model. Okay, we can estimate the complexity of the model. Now here you can see, here we have f by f dimension. This is the dimension of the filter. Here dimension of the filter is f into f. Okay, now what is k here? K is the total number of filter that have been used for convolution operation. So what will be the dimension of the filter in this case? So if we are having c number of channels with the input dimension of the image of dimension of the input image, so here the dimension of the input image is I into I, and here c is the number of channels. So therefore input volume becomes I into C. Okay, and output size becomes O into K. Why K? Because since we are using K number of filters, so therefore for one filter we will obtain O into O dimension feature map, and for K number of filter that we are using for convolution, so therefore the output volume of the feature map becomes O into K. Okay, and if we stick to this dimension of the input volume as well as the output volume of the feature map, including the dimension of the dimension of the filter and the number of filters that we consider, then the total number of parameters will become f into c plus 1 into k. Okay, so for one filter, if we convolve one filter with the input volume of the image, then this will give us the number of parameters, give us f into c plus 1. Okay, so c is the number of channels. So grayscale number of channel is 1. For RGB color image, the number of channels become 3. Okay, now for one filter, if we convolve one filter with the input volume of the image, then we will obtain f into c plus one number of parameters. Now since we are using k number of filters for convolution, therefore this will be multiplied by k. Okay, so this will be the total number of parameters that can be determined when we have the input size and output size like I into C, O into K. Okay. Now you will ask this, why we are using this one, why we are adding this one. Now this one is used for the bias parameter. Okay. So there will be one bias parameter per filter. So if there are k number of filters, then there will be k number of bias parameters. So this will be multiplied by k, that we are doing here. So in most of the cases, what we see that the dimension of the stride or length of the stride will be found to be length of the filter. And the common choice for practical application will be K is 2 into C. Okay, that means the number of channels. If we have number of channels, if we have number of channels become 3, then 3 into 2. That means the K will be 6. So K will become 6. So 6 means 6 number of filters we have to use for the convolution operation. Okay, so this is a common choice for any application. Now for large application, so for commercial application, we can find the number of K is very large. That means number of K is very large means where we have get the images in batch size. Okay, so according to the batch size, the number of K will be determined. Okay, now here in case of the pooling operation, this is the if we consider this is the dimension of the dimension of the pooling matrix F by A. So here we get the number of parameters 0. Okay, and in this case, the input size and the fully connected layer, the input size will be considered n in. Okay, and output size considered n out. Then the total number of parameters become n in plus 1 into n out. N in means what? N in means the number of neurons in the input layer. And what is N out? N out is the number of neurons in the output layer. Now, if there are two layers, if we consider the simple fully connected layer, then we will have total number of parameters as N in plus 1 into N out. Okay, and this one is used for bias. So per neuron means for one neuron we can use one bias. Okay, so total number of bias becomes n in plus 1 into n in. So this will become n in plus 1 into n out. Okay, this is the total number of parameters, and number of biases would be n out. Okay, so number of biases will be equal to n out. Now here we can see how to determine the receptive field. Now if we know the if we know that kth layer represent in the convolutional neural network, and the dimension of the receptive field becomes Rk into Rk. Okay, so at kth layer we can denote the receptive field as Rk into Rk, and here Fj is the filter size. Okay, here Fj is the filter size of layer J. So at jth layer we can get the filter dimension Fj by Fj. Okay, and Si is the stride value of layer I with. So if we consider if we consider here F1 equals to F2 equals to 3, that means the filter dimension is in two different layers. The filter dimension is found to be identical, 3 by 3 and 3 by 3, and stride length is in both the layers. The stride length is found to be 1. Okay, so here we are having two stride, here we are having two filters of having identical dimension. Then what will be the dimension of the receptive field? Okay, so if we know the filter dimension for convolution operation, if we know the stride length, then we can determine what will be the receptive field that will decide the neighborhood area in the input image. Okay, so here this is our filter, this is the input image. Okay, now with the length of the stride and with the dimension of the filter, we can decide what will be the dimension of the receptive field. So in this case, we have determined the dimension of the receptive field in the second layer. Okay, what is second layer? What is the second layer? This is the second layer. This is first layer. Okay, so here in the second layer, the dimension of the receptive field becomes 5. Okay, so 5 by 5. So here we get the 5 by 5. Now if we consider that if we consider this is okay, let us consider in another way. This is the input image, this is the filter, and here we get the convolution operation between filter and input image, and the receptive field dimension is found to be 5 by 5. Now, when convolution operation is done, the feature map is obtained as 4 by 4 dimension. The dimension of the feature map is found to be 4 by 4 dimension. Again, the same dimension of the filter is used for convolution operation with this feature map. Okay, with this feature map. And when the convolution operation is done, so we obtain 2 by 2 dimension of the feature map in the output. Okay, so in both the cases we can decide what will be the dimension of the receptive field, and this receptive field will decide what will be the neighborhood area in the input image as well as in the generated feature map. Okay, so in both the layers we can decide the dimension of the receptive field, and accordingly the dimension of the neighborhood will be decided in the input image as well as in the feature map. Okay. So now we will talk about the activation functions. Now activation functions can be what? Now what is activation function and why we use the activation functions? So we use the activation functions to map the resulting output in the range of 0, 1 or in the range of -1 and 1. That means whenever we generate the output in the neural network, so the output the output will be in the range of 0, 1, 0, 1, or will be in the range -1, 1. Okay. Now activation functions can be divided into two different groups. One is called first group is called the linear or identity activation functions, and second is the non-linear activation functions. Now what is linear activation functions? In linear activation function, the output of the function will not be confined between any range. Okay, any range. That means we cannot decide, if we want to decide that the output of the functions or output of the neural network functions will be in the range of 0, 1, then we cannot consider the linear or identity activation functions, because the linear activation function will give the same output as that of the input. So therefore we can get the output in any range. But if we consider the nonlinear activation functions, then we can bind the output in between 0 and 1, just like the probabilities value. Okay, so if we are working with the multi-class classification, then these probabilities values will decide the proximity of the class belongingness. So we are interested to generate the probabilities in the output using nonlinear activation functions. So in most of the time, almost in 99%, we use the nonlinear activation functions in neural network as well as deep learning neural network. Okay, so nonlinear activation functions are the most used activation functions. Now why we use the nonlinear activation function? Because it will make the model more generalized, or it can adapt a variety of data in order to differentiate between the output. Okay. Now to understand the nonlinear activation function, so we can use two different terminologies. One is the derivative or differential, and another is the monotonic function. Now, what is derivative? So, derivative or differential means we want to have the change in y-axis with respect to change in x-axis, and this derivative or differential change of y with respect to x-axis is known as slope. Okay, as known as slope. And what is monotonic function? So monotonic, what we know about the monotonic function is that the monotonic function will be either entirely non-increasing or non-decreasing. Okay, not partly, entirely the function will be non-decreasing or non-increasing. And nonlinear activation functions are mainly divided on the basis of range or curves. So when we talked about multi-layer perceptron neural network, so there we saw that every neuron, every nonlinear activation function like sigmoid activation function or logistic activation function is associated with each neuron in the hidden layer, and in the output layer we can use the softmax activation function, because softmax activation function generates the probabilities for different classes in case of multi-class classification in order to determine the proximity or the belongingness of the class of the input sample or some unknown sample that we want to predict the proximity belonging to a particular class. Hence, the nonlinear activation functions are mainly divided on the basis of range or curves. Okay. So first activation function that we will talk about, the sigmoid function. Now, what is sigmoid function? Now, sigmoid functions will look like the S shape. Okay, the shape of this sigmoid function or logistic function is S shape. Okay, and here you can see that this is not the zero-centered. This is not the zero-centered activation function. Okay, and the output of the function is bounded between 0 and 1. So this is 0 and this is 1. So maximum value of the output will be 1 and minimum will be 0. So in between 0, the output will be generated, and whatever the output will be generated, so here this is the intersecting point and of the y-axis of this curve, and this point is decided as the threshold. Okay, if we decided the threshold is t, then whatever the output value will be coming in the output of the network, so based on this threshold, and whenever we compare the output value with the threshold, so that will decide what will be the class level. So in most of the cases, when we use the sigmoid function, so sigmoid function can be used for the binary classification, because if we get the values above 0.5 or only 0.5, then we can decide the class level to be 1, or if we get the output value less than 0.5, then we can get the class level as 0 or negative. So this function, this activation function, this sigmoid function is found to be differentiable between any 2 points in the activation function. And this function is also found to be monotonic function, but the derivative of this function is not monotonic. Okay. Now, if we take the derivative of this function, sigmoid function, then this sigmoid function, derivative of the sigmoid function is not found to be monotonic, but the sigmoid function itself is a monotonic function, and this function is found to be differentiable function. Now the next activation function is softmax function. As I said that this softmax function basically used to generate the probabilities in the output layer for multi-class classification, and here the softmax is found to be more generalized form of the sigmoid, because we can use the same form of the sigmoid function here, but here we can normalize the value, and by normalizing the value we can get the probabilities between 0 and 1, and these probabilities will give us the proximity of the class belongingness of the input samples. Next activation function is tanh function. So this is the modified form of the sigmoid function or logistic function. In this activation function, we can find the function is zero-centered function. So zero-centered means the maximum value of the output will be 1, and minimum value of the output will be -1. So this is the range of the output that will be generated by the network. Okay, -1 to 1. So this is the range of the tanh activation function, and this is called the zero center, because here the function, the SF function, is passing through this origin. Okay, so therefore this is called the zero centered activation function. The next activation function is rectified linear unit, or in short we call ReLU activation function. Now the ReLU activation function, if we see the shape of this ReLU activation function, then we can see that the range of this activation function is found to be 0, infinity. Okay, so this is another nonlinear activation function. Now what happens here? Here, whenever we get some negative value in the output, so that negative value turns to be 0. Okay, and whatever the value we get as maximum between 0 and z, so that will be considered as the output of this output of the function gz. Okay, so gz becomes the maximum of 0 and z. So if here we get any negative value, so that will become 0. Now what happens? So in this case we can get the large number of negative values, and these negative values, large number of negative values, when the large number of negative values become 0, then we cannot make the network learn further. So this is the main problem with ReLU activation function. But ReLU activation function is found to be differentiable as well as monotonic. Monotonic means the function itself is a monotonic, as well as the derivative of the function is also found to be monotonic. So both the properties are satisfied by this ReLU activation function. But as I said that there is a problem with there is an issue with ReLU activation function, so which can overcome by another modified ReLU activation function, which is known as leaky ReLU. Leaky ReLU means here we can consider the small number of negative values. Okay, small number of negative values, and this range of this function becomes -1. Here the -1 to infinity. Okay, so here we get the 0 to infinity. Here we get the negative to infinity, not -1. Negative to infinity. That means small number of negative values that found 0 in the ReLU activation function are taken into consideration in leaky ReLU activation function, because some negative functions will be used for the learning the network further. We have another modified ReLU activation function, which is known as the LU. Okay, which is known as the LU activation function. So LU activation function, the formulation for this LU activation function is this. So here we are considering. So if you can look at the shape of this LU activation function, then you can understand this is found to be differentiable everywhere. Here we also consider the negative values in different way. That means here we are getting some uh, more values, more negative values, but in different way. So what is the way? Way is that we are using an offset. Okay. So this is the offset. Alpha here is the offset, and to adjust the output value, we can use this offset in the LU activation functions. And here LU, leaky ReLU, and LU, these three activation functions are found to be differentiable as well as monotonic. Okay, monotonic. As I said that these three ReLU function is monotonic itself is a monotonic functions, as well as the derivative of the ReLU function is also found to be monotonic. So same as that of ReLU function, leaky ReLU function and LU functions are also found to be monotonic themselves, as well as their derivatives are also found to be monotonic. Okay. Any questions? If you have any questions, you can ask me. So today is the last class. So in the next week we will not have any more class. And if you have any doubt, so you can let me know in the next week, so that we can arrange another online meeting for doubt clearing. Okay. Okay, that's all for today.
Thank you.